So that's getting set up. Now I will record to the cloud. As usual, if you don't wish to be recorded, then you should mute yourself and turn your video off. I'm going to spotlight you, Jean-Christophe, and you should feel free to start whenever you're ready.
All right, so thank you very much. So welcome back, everybody. As announced yesterday, now we're going to start chapter 1, talking about large deviations and convex analysis. So these are very wide topics, but we are only going to focus on a selection of results which will be at least informative to what comes next. Not necessarily crucial, but informative. And to start with large deviations, I'm going to focus on an example where we can compute things explicitly. And so I'm going to focus on the case when we are looking at the sum of independent Bernoulli random variables. So I'm going to write xn for these variables. So independent Bernoulli, and so they take the value 1 with probability p, and the value 0 with probability 1 minus p. So the mean value is p, and we know from the law of large numbers that if I compute the sum, I'm going to write the sum S capital N. So 1 over n sum little n from 1 to capital N of xn. This we know is converges almost surely to p as n goes to infinity. And the question large deviation asks is, before we are at the limit, how does the probability that Sn is equal to something other than p behave? So surely it will go to 0, but can we specify exactly how? And this question is not answered by the central limit theorem, because the central limit theorem tells us about deviations from p over the 1 over square root of n. But here we are asking about deviations over the 1. So that's why it's called a large deviation. So the typical deviation of Sn is over the 1 over square root of n. And this is, here we are going to ask about order 1 deviations. So yes, in this context, we're going to be able to compute things exactly, essentially, because if I ask myself, what's the probability that Sn is equal to k over n for k between 0 and n, then the answer is just n choose k, and then p to the k, 1 minus p to the n minus k. I think this is clear. And so I want to understand this, how this behaves when n goes to infinity and k over n remains in the neighborhood of some fixed value. So in order to do that, I'm going to use an equivalent for k factorial, just to simplify this combinatorial factor. And so this is a simpler version of Stirling's formula, if you want. This is the same as the exponential of k log of k over e plus a small correction over the logarithm. Of k. So I'm going to think about k over n as being at least close to a value which stays away from the boundaries of the interval, so away from 0 and n, and sorry, 0 and 1, and let n go to infinity. So let's say denote I'm going to be a little bit informal in this derivation, but hopefully you can make more precise sense of it if you want. So x, I'm going to write x instead of k over n. And I'm going to assume that, so assume, just to make the computations rigorous, I want to assume that x is away from 0 and 1. By this, I mean that you should think that k and x will maybe change a little bit as n goes to infinity. But I want to think of x as being essentially fixed, except for this constraint that it's an integer divided by n. And I want to make sure that uniformly over this going to n go to infinity, x remains, let's say, at distance delta away from 0 and 1. Okay. And so with this convention, this combinatorial factor, this n choose k, I can rewrite as, so this is n factorial divided by k factorial n minus k factorial. So if I use this equivalent above, this will be n log of n over e. This is the n factorial. And then there's the k factorial. So k, I'm going to write nx. And then there's the n minus k factorial, which I'm writing as n 1 minus x. And maybe I'll smuggle in the error here. Okay, so because I assume that x is away from 0 and 1, the error term will be over the big O of log n. Okay, just to make my life easy. And we see that there are simplifications in this expression. Maybe initially you think that this is in the exponential, it looks like there are some n log n terms, but you see that they simplify. If I expand the logarithm here, I have n log n here, and if instead of log of nx here I write log n plus log x, I will have nx log n and then n 1 minus x log n. So all of the n log n's will disappear. Okay, so I want to, I want to clarify that this indeed happens. I'm going to rewrite this expression. And similarly, the 1 over e guys, they will also disappear for the same reason. Okay, so what I end up with is minus n x log x minus n 1 minus x log 1 minus x. And then still my error with the O of log n. So far, so good. So recall that I'm doing this computation about this combinatorial factor because I want to understand this probability here. Okay, the probability that Sn is equal to x, in fact. So in this expression, there is the combinatorial factor, and there's this p to the k, 1 minus p to the n minus k. So let's bring back this p to the k and 1 minus p to the n minus k in the computation. Let me just oops. So p to the k, I'm going to write this as exponential of k log p, and k is nx. So if I want, I can, by bringing this term together with the term above, this is going to be, I can write this as nx log of x over p. Maybe I'm going to bracket this like this. And the other term will be of similar form. So then we have 1 minus x log of 1 minus x divided by 1 minus p. Okay, and then the error term. All right, so that's the end of this computation I wanted to do. I'm going to give a name to this term. Where is it? So this thing here, I'm going to call I of x. Okay, so when I write equal to dots, it means by definition. Okay, so I define I of x like this. So if you plot I of x, it looks like this. Okay, let me try to do a decent plot. Okay, so it's defined between 0 and 1. And okay, it's some value at 0, it's some value at 1, and it vanishes at p, because that's easy to see. So, I mean, and also we kind of expect that, okay, maybe it's not completely obvious, but the probability that Sn is equal to p or in some, at some value very close to p is actually sub-exponential. And any other, if you ask it to be, I don't know, let's say if p is 1/2, and you wonder what's the probability that Sn is actually 0.6, then this calculation reveals that this probability is exponentially small in n. And moreover, it tells you exactly what coefficient in the exponential varies. Okay, it's this I at 0.6. Does that make sense? And notice also that this function I is convex, in fact, strictly convex. Okay, so if I summarize this calculation, so let's say conclusion. Let's say if I want to be a bit precise with my x being away from 0 and 1, I can say for every delta positive, if x is between delta and 1 minus delta, so let's say delta is small, okay, otherwise x is it doesn't really make sense to ask for this. And is of the form k over n for some integer k. Then p Sn equals x is exponential of minus n I of x plus big O of log n. And the big O depends on the delta, as I have written in there. Oh yeah, that's a nice tip. Thanks, Luigi, for this comment. All right, so that's the first thing I wanted to say. And the second thing I want to say is that perhaps we want to ask other questions than, so if I again think of P as being 1/2, instead of asking Sn to be in a neighborhood of 0.6, maybe what I care about is only that Sn is at least 0.6, but I don't mind if it's much bigger than 0.6. So what about, so let's say for any x between p and 1, we can observe. So, if I try to understand the probability that Sn is at least equal to x, so the computation I'm going to do now should evoke this exercise 1 in the first problem set, because I'm going to say that these quantities, you can think of it as a sum of exponentially unlikely terms. And in fact, whether you look at the sum or whether you look at the maximum of these terms, in the limit of large n, the behavior is the same. Okay, so I'm going to do these observations here. So here I can, if I want to start with the lower bound, I can just replace this by the probability that Sn is equal to, let's say, the integer part of nx. This is the largest integer at least equal to nx divided by n. And this we have just seen behaves like exponential of minus n I of this quantity, nx divided by n plus O of log n. And this function I is continuous. We have seen the explicit expression. And in fact, it's differentiable. So I can insert the error here. If I replace this I of the largest integer, etc., by just I of x, the error is over the 1. Okay. So after I multiply it by n, so I can just put it into the error term. So in fact, you see that if I ask the probability that Sn is equal to x, or if it's larger than or equal to x, basically I get the same behavior. Okay, and this is the large deviation type event. Asking that it's at least equal to x will be realized by basically making Sn be equal to x. So that was the lower bound. If I want to fully justify what I said, I should also prove the converse bound. Let me do this. So it's really in the spirit of this exercise 1. This I can bound by the sum of the terms. So let's say that this time I'm going to take the smallest integer. Sorry, the largest integer below or equal to xn. And okay, so I'm not going to justify this very carefully, but at least intuitively. So here we're having x above p. So this function probability of Sn equal to k over n will be increasing with k. Okay, so here I can bound this by the number of terms, and I'm going to brutally bound the number of terms in the sum by n. Okay, maybe I should even write n plus 1 times the probability that Sn is equal to the first of these terms, xn divided by n. Okay, so this is by a monotonicity property, which I don't justify, but you can verify if you are patient. Okay, and now again, we know that this probability behaves like exponential minus n. Okay, and I'm going to directly write I of x this time. Okay, so for the same reason as before. And again, this n plus 1 in front, I can absorb into the error term. Okay, so the conclusion of these computations is that for every x between p and 1, we have that the probability that Sn is larger than or equal to x is exponential of minus n I of x plus O of log n. Okay, and you can verify that similarly if you ask yourself what happens for x below the mean value. So for every x between 0 and 1 and p, sorry, the probability that Sn is less than x is going to be exponential of minus ni of x again, plus some error term. Okay, and the whole reason for this is exactly in the spirit of this first exercise of the problem set, okay? Because whether we're keeping a sum of terms or the maximum of the terms, the behavior asymptotically is the same. And just to clarify, in this derivation, what I don't care very much what's the exact form of the error term. Okay, what I want to display is just the leading behavior, like it's exponential minus ni of x. And so I'm going to suggest another exercise, which is not part of the problem set, but using these observations above. So here we have studied the probability that Sn belongs to the interval x plus infinity or minus infinity x. And the claim here is that you can generalize this to arbitrary measurable sets in the following way. So for every measurable set, if I look at the lim sup as n goes to infinity of 1 over n log so when we look at arbitrary sets, so I'm not sure what, so I see a question in the chat, how did I arrive at this conclusion? So let me back up for a second. So this is the consequence of the two bounds we have proved just before, okay? So we had, I study, so we start from this quantity, we have this lower bound, and then we also have the converse bound. Okay? So if I combine the two bounds, I get the result. Sounds good. Everything is absorbed into the error term. And I did not explain for this side, but it's the same. It's the same argument, except you have to think about x being below p. All right, so let me come back here. So when we look at arbitrary sets, we have to be a bit more careful. And so when we try to write down an upper bound, it's convenient to replace the set by its closure. So it's clear that the probability that Sn belongs to the closure of A will be something larger. And then I'm going to use a bound that refers to this closed set. So this is going to be smaller than the if of I of x for x in the closure of the set. Okay, so A bar means the closure of the set. Okay, so I claim it's possible to show that this is true. And for the converse bound, so here I'm going to use the interior of the set A as the lower bound. So it's clear I can replace A by its interior and get a lower bound. And from there, I claim that this object is bounded from below by the inf of I of x for x in the interior. Okay, so this notation, this is the interior of A, and this is the closure of A. Ah, okay. I see another question in the chat. It's okay. So I come back to this calculation. So the question in the chat is about this passage. So as written in the chat, it's not true. What you wrote in the chat is not true. But what I wrote here is true, because O of log n absorbs this n plus 1 term. Okay, n plus 1, you can write this as exponential of log n, and then you have just an extra log n. Okay, so it's just absorbed into the big O of log n. All right, let me come back here. Okay, so it's important to, one has to be a bit careful when we try to make statements which talk about general sets, because for instance, you see that this Sn, it takes only values which are of the form an integer divided by n. So if you're nasty, like if A, for instance, is the set of real numbers, take away the rational numbers, Sn will never be in the set. But if you take the inf of I of x over this set, you will get 0. So you'll have a contradiction in your estimate. So in order to avoid this, you have to take this interior or closure, depending on the bound you want to state. Okay, and this is the formulation of a general large deviation principle for the random variable Sn. Okay, so I'm going a bit faster on what large deviations are, and I'm sorry I have to make you swallow all of this, but okay. I hope you take some message out of it, even if I am a bit fast. So whenever these two conditions are satisfied, we say that the sequence of random variables Sn satisfies a large deviation principle with speed n and rate function I. So the speed is what appears here. Okay, so informally you can write, let me write informally. The probability that Sn is equal to x, or maybe is close to x, is like exponential of minus n I of x. Okay, and the speed is what shows up here in this exponential. Okay, the exponential of minus is n, that is the speed, and then I of x, that is the rate function. All right, so even though I was kind of quick, I gave a justification of the fact that this sequence of Bernoulli random variables, independent Bernoulli random variables, when we compute this, the sum of these random variables, this sum satisfies a large deviation principle with speed n and with a rate function which we found, which is this this function I call I. Okay, and we did so using explicit computations, basically based on Stirling's approximation. Now this is nice, but you may ask, what about other random variables? Let's say bounded random variables, but still independent and adensely distributed, and we still compute the sum. So what about more general random variables. So say that oops. I'll just say bounded to make it convenient, to not worry about integrability questions. And let's say they are centered also without loss of generality. So independent and identically distributed random variables. And let's say that X is non-negative. And maybe I also take a parameter, lambda. Okay, maybe forget about this for now. X is non-negative, and I want to understand the probability that, so Sn is defined as before, okay, 1 over n, the sum for k equals 1 to n of xk. And I'm asking, what's the probability that Sn is larger than or equal to x? I would like to recover a result similar to the one we found for Bernoulli random variables. And let's say for now that I want to find an upper bound. Okay, so I want to find an upper bound. So one thing I could try to do is use a Markov's inequality. I could say, oh, this is smaller than the expectation of Sn divided by x. Okay, let's say that x is positive. That's true, but that's not very nice because, well, no, that's not true because Sn is not non-negative. So maybe I should do a second moment instead. Okay, so if I do Markov inequality with the second moment, I will write on the right-hand side expectation of Sn squared divided by x squared. Okay, and expectation of Sn squared, it behaves like 1 over n. So it's interesting, but it gives me a bound which decays like 1 over n as n goes to infinity. But in view of what we've done with Bernoulli random variables, we know that at least for some random variables, this decay is actually exponential in n. So this bound we get like this is not good enough. And so you say, okay, first moment that was wrong. I mean, I should have taken absolute values for Sn. Second moment gives me 1 over n. Maybe I could try the fourth moment of Sn. Okay, so I compute the fourth moment of Sn, and I get so the bound would be expectation of Sn to the 4 divided by x to the 4. And here I would get a bit better, but still polynomial in n. So we seem to have some improvement, but we are not getting far enough. And in fact, here the idea is to use the exponential function to do this Markov inequality argument. So let me write it down. We're going to write this as I can write it like this. So let's say I fix lambda non-negative. The exponential function is non-decreasing, so this is correct. And now I use Markov's inequality. So this is smaller than the expectation of exponential lambda Sn divided by exponential of lambda x. And now I should remember what is the definition of Sn. So okay, let me keep the exponential minus lambda x, and then oh, and I want to put an n. Sorry, I forgot. Let me insert an n in front here because I want to see exponential decay. It would be good for me to put an n here. Okay, so this makes me happy because I see exponential decay in n already, and hopefully I can do something with what's left. So lambda n Sn is lambda times the sum of the variables. So E of lambda x1 plus plus xn. So the exponential function is doing two things which are very nice to us. Perhaps most importantly, it seems to show promise for giving us exponential decay in n, which is what we want. And secondly, it does some other thing which is very nice, which is that when the variables are independent, we see that this expectation can be simplified. The exponential of the sum is a product of the exponentials. And then by independence, we can rewrite this as the product of the expectation. Okay, so this is the same as exponential of minus lambda n x times the expectation of exponential lambda x1 to the power of n, which I'm going to rewrite as exponential of minus n, then parentheses, lambda x minus psi of lambda, where psi of lambda being defined by the logarithm of the expectation of the exponential of lambda x1. Okay, so yesterday I had announced that we would see Laplace transforms showing up already with large deviations. So here is a Laplace transform. Okay, we could call this the Laplace transform or maybe log Laplace transform of the random variable x1. And I think I missed the parentheses here. So if you're with me here, I started trying to estimate this probability that Sn is larger than or equal to x. And I did this calculation, and this calculation is valid for any lambda non-negative. So now that I see this, I should make my bound as good as possible, and this is by taking the infimum over lambda on the right-hand side. Okay, now if I take the infimum over lambda, so we have shown that the probability that Sn is larger than or equal to x, this is always smaller than the exponential of minus n. So I take the inf over lambda. Yeah, they are identically distributed. I'm not assuming that they are equal. So exponential minus n times the supremum over lambda non-negative of lambda x minus psi of lambda. Okay. And in fact, what's really remarkable is that this computation, which maybe looks a little bit ad hoc when you first see it, because we just decide we're going to use the exponential function, in fact, is asymptotically sharp, in the sense that if you look at this probability, you take the log, you divide by n, and you ask what is the limit. In fact, the limit is indeed minus this supremum. Okay, and this is the more general version of large deviations for independent and identically distributed random variables. Yes, exactly. And so more convex analysis is showing up. So let me denote. I'm going to use a notation for this supremum over lambda. So when you give me a function psi, I'm going to write psi star for the function defined like this. So the supremum over lambda, in fact, here I take lambda in R, of lambda x minus psi of lambda. In the computation above, in the computation here, it's only sup over lambda non-negative which appears, but we had x positive. So you can show that when x is positive, because the variables are centered, taking the sup over lambda non-negative or the sup over lambda in R is the same. I think there is a proof of this in the handwritten notes, but it's not very difficult to show. So really what is showing up here, this is really psi star. And indeed, as someone wrote down in the chat, this is some people call it Legendre transform. I will just call it the convex dual of the function psi. And no, this is like, the limit. So the claim is that, so let me write down the precise theorem now, and then I'm going to answer the question in the chat. So here is the theorem, which I have not proved now. I only proved one bound. But here is a theorem. So it's large deviations for IAD random variables. So let me. So independent and identically distributed random variables. And for convenience, I'm going to assume that this Laplace transform is finite for every lambda. This is not really necessary, but I just want to make my life convenient. For every lambda in R. And define this Laplace transform, psi of lambda, to be the log of this quantity. Okay, so maybe I could fancy to call this the free energy of x1. I'm not going to do it. I'm going to stick to Laplace transform. And again, we define the psi star as above. Okay. Psi star of x is the supremum of lambda x minus psi of lambda. So the claim is that the random variable Sn, which is 1 over n sum of xk, satisfies the large deviation principle. With speed n and rate function psi star. So is the statement clear? I was quite fast in even defining what large deviation means, but yes. So now I can. So if the statement is clear, then I can comment on the question in the chat, which is, can we use other functions than exponential in the derivation above? So I mentioned you can use the square function or many other functions, and the next comment in the chat confirms this. It's true. But if you want to identify the correct behavior as n goes to infinity, so this theorem I have not proved, but it says that this quantity we observe that shows up when you use the exponential function, this psi star, is in fact the correct number. It is the correct value for the limit of 1 over n log of the probability. So you can use other functions, but if you want to put your finger on the right limit, then you'd better use the exponential function. In fact. Is the statement at least sort of clear? I'm not going to be super precise, but maybe it's a good time for a little break. So let's take 10 minutes of break, and I'm very happy to answer more questions if needs be during the break. Yes, yes. So you don't need to assume that it's finite everywhere. Like I think it's if you assume that it's finite in the neighborhood of the origin, that will be enough, for instance. And if you don't assume that it's finite in the neighborhood of the origin, I think then the statement no longer makes a lot of sense. So then the function will be finite in the neighborhood of the origin and infinite elsewhere. But you can still make sense of the convex dual. You know, when you take this supremum, the quantity in the supremum will be either finite or minus infinity, but you just ignore these values of lambda for which psi of lambda is plus infinity. So it's psi star is still well defined, and the statement is still valid. Haha, another good question. So if we take the question, what's the relationship between psi star and this function I of x we discussed at the beginning? So this is a very interesting question, and I'm going to perhaps a bit nastily add it as a little exercise. So verify that if you take x1 to be Bernoulli with parameter p as in the beginning, then you can define this function psi for x1, and then you can define psi star. And this psi star should be I, right? So I use it, I say it is an exercise, but it's in the notes, in fact. And if you look at the notes, at the handwritten notes, you will find it. So if it's not, yeah, but it's nice to rederive it because I find it cute, at least. I find it nice. This question is more philosophical. I'm not sure how to address it. Maybe if you can, difficult to. So just as a side comment, going back to the previous question, another case where it's nice to compute the large deviation rate function is when you take x1 to be a Gaussian. In this case, this log Laplace or this Laplace transform is just a lambda square over 2. If let's say they are standard Gaussians. And the convex dual of lambda square over 2 is x square over 2. So for Gaussians, the rate function is x square over 2. You can compute large deviations for other functions. Yeah, sorry. Thanks for yes. So this is large deviations exactly for the reason Luigi says. Yeah. And yeah, so I could also make a parallel with something Luigi mentioned yesterday. So yesterday Luigi talked about universality. So the central limit theorem is an example where we have universality, because any random variables we take, we see this Gaussian showing up in the limit. But large deviations is not of this sort. You know, the behavior of the large deviations really depend on the law in some more intrinsic way. You know, there's no, like for instance, you know, for Bernoulli random variables, the rate function is this function I of x, and for the Gaussians, I just said that the rate function is x squared over 2. So we see that there is no, let's say, disappearance of the microscopic details when you ask about large deviations. And it sort of makes sense, you know, for like to make it even more vivid. When you take these Bernoulli random variables, if you ask for the sum to be, you know, this sum normalized by n, if you want it to be larger than 2, let's say, this is impossible. Right? It's not possible that when you sum these Bernoulli random variables, n of them, and you divide by n, you get something which is larger than 2. Okay. While for Gaussians, it is actually possible. So, and So it's clear that there are some differences between Bernoullis and Gaussians in this case. Yeah, I had missed. Oh yeah, so another question is about Markov chains. So here I would suggest to consult. I think it's so you can find in. So the most fundamental reference for large deviations is the book of Dembo and Zaitouni, which is extremely comprehensive. But if you want to know about Markov chains, you can also look into the book of Dan Hollander on large deviations. I think both have the title large deviations. And I think the book of Dan Hollander is more accessible. And I think it does cover Markov chains. It's a very nice result to derive what is the rate function for Markov chains. Both are large deviations. Both the titles are large deviations. Ah, yeah, I should type it. So Dan Hollander is as written in the chat by Omer. And shortly, I'm going to state a more general result than the one which is currently displayed. And I'm not going to take time to prove it today with you, but if you go to see the handwritten notes, there is a proof there. So in particular, you can find a proof of this result about IID random variables from the notes, but it does not. This does not cover Markov chains. Yes, that's right. So another question in the chat is, what does it mean, this satisfying a large deviation principle with speed n and rate function psi star? Yes, it means exactly that these inequalities we have seen here are valid, except you replace I by psi star. Thanks for the question. This is quite important. All right, so I'm going to resume. So in fact, at least as far as this upper bound is concerned, we can imagine, so I want to imagine a generalization of this statement, which does not necessarily assume that the variables are independent. And we will see, I want to display it because, okay, I'm going to state the result, and then I'm going to explain exactly why I think it's interesting. So let's suppose for a moment that now we have this random variable Sn, but it does not have a super obvious decomposition into a sum of independent random variables. It's just some random variable we care about. We would like to understand its large deviations, but it does not have an obvious sum of independent things structure. We can still apply this inequality that is on display here. We can still, oops, sorry, here. Okay, this is still okay. Why not? And so what was nice with when we had this decomposition of Sn into a sum of random variables is that we could compute this Laplace transform of n Sn. But perhaps instead I could just postulate that this function has a limit when n goes to infinity. No, it's kind of clear that it does have a limit. Okay, after I take the log and I divide by n. This thing we said it's okay. If we track, I'm focusing on this function here. So it reappears here, and so when we had this sum of independent random variables, it's clear that this quantity, is something to the power of n. So if I take the log and I divide by n, it's just constant. So what I want to do now is actually just postulate that this object has a limit and see if I can derive large deviations just out of this. Let me state the result. So the result I'm going to state is some version of what is known as the Gardner-Ellis theorem. I don't know if it's stated exactly the way I'm going to state it anywhere, but basically it's the Gardner-Ellis theorem. So let's say general LDP. So it's a more ambitious statement because now I'm not assuming that Sn is a sum of IID things. Okay? It's just some random variable. Let Sn be a sequence of random variables. Let's say they are real valued. And define, oops. Psi n of lambda, which is this Laplace transform. So 1 over n log of the expectation of exponential lambda n Sn. Okay, so if you assume Sn are sums of random variables divided by n, this is actually a constant. So what I'm going to assume instead is that this thing converges to some function. So assume that psi n converges pointwise to some function psi psi in C1 of R. Okay, so in particular, it has to be finite for n large enough, okay, because I assume it's converging to some well-defined function from R to R, and on top of that, I assume that psi is a C1 function. So I claim that under this assumption alone, you have your large deviation principle with speed n and rate function psi star. So psi star defined as before. Okay. Maybe I can rewrite this again. So psi star of x, sup of lambda x minus psi of lambda. It's really the same definition as before. It's just that oops, not x lambda. We had the break in between, so maybe it's good to rewrite it. Define psi star like this. Then Sn satisfies the large deviation principle with speed n, oops, and weight function psi star. Okay, and because there are many things I want to speak about during these lectures, I'm not going to explain the proof here with you on the slides, but I wrote the proof in the handwritten notes. And maybe if people in the collaborative LaTeX team are motivated, maybe ultimately it will be also typed. I don't know if that's maybe quite some amount of work. But anyway, there is a proof somewhere. And I suppose it's best to look at the notes because it's perhaps harder to locate a specific reference where this exact statement is proved. Okay, so if you so what we have shown, okay, at least almost shown, is that the upper bound is okay. You know, we have done this argument. You can massage it a bit and get the upper bound. But what's remarkable is that this bound is sharp. Yes. So the speed is because the speed n is because we put n in these slots. So if you replace n by something else, you can have different speeds. But in some sense, yeah, without loss of generality, we can basically normalize things so that it's like this. Because here Sn is, I don't even say anything about it. So then the convergence of this psi n will be problem specific. But what I really want to emphasize here is that this assumption that psi is C1, it looks like maybe it looks like we don't even notice it, or maybe it's just like some convenience in the proof. But in fact, it's fundamental in the sense that if you don't assume that it's C1, if it's just a continuous function or even just a Lipschitz function, then I can find counterexamples. And this is one of the things I wanted to emphasize here, because this, later in the class, we will see in other circumstances, this assumption of assuming that something is C1 being important. And I think it's nice to know that even at the level of classical large deviations, this assumption is actually already showing up. So I want to illustrate for you the fact that this assumption is important. So I'm going to give you an example where psi is only Lipschitz, and therefore, and also the large deviation thing is false. So let me. So it's a counterexample not to the theorem, because the theorem is valid, but it's a counterexample to the situation when psi is only Lipschitz. So let me just, I want to assume that, so here I can choose Sn exactly the way I want, right? There is no constraint. I don't need to assume it's a sum of independent things. So I'm going to build my counterexample like this. So suppose Sn is such that it takes the value 1 with probability 1/2 and the value -1 otherwise. Okay, and let's imagine I'm trying to apply the result I displayed to this circumstance. So then, if I compute this function psi n of lambda, it will be 1 over n, the log of the expectation of exponential lambda n Sn. So it's going to be log of 1/2, this is the 2, exponential of lambda n, okay, times 1 plus 1/2 exponential of minus lambda n. Okay, when n goes to infinity, what will happen is that if lambda is positive, this sum will be completely dominated by the first exponential, and in the end we'll just see lambda as the limit. On the other hand, if lambda is negative, then it is this term which will dominate, and we'll only see minus lambda as the limit. So to summarize, the limit of this object is going to be absolute value of lambda. Okay, so this is going to be our psi of lambda. And as announced, this function, this limit function psi of lambda is Lipschitz, but it is not C1. Okay. Now, let's see if the large deviation principle with right function psi star is valid. So I have to compute psi star now. So psi star of x, oops, I'm sorry for the bad notation, bad writing. By definition, this is the supremum over lambda of lambda x minus psi of lambda, and psi of lambda, we said it's absolute value of lambda. So if x is between -1 and 1, then it does not pay off to move lambda around, because you know, let's say x is 1/2, for instance. Then you would maybe try to increase lambda a bit, but you're paying minus absolute value of lambda. So your best choice for lambda is lambda equals 0. So this is 0 if x is between -1 and 1, and it's plus infinity otherwise. Okay, so let's say, for instance, if x is 2, and you're having this supremum of 2 times lambda minus absolute value of lambda, then you can shoot lambda to infinity, and you see that the supremum is plus infinity. So if we were to believe that large deviations is valid with this right function, it would say that whenever x is between -1 and 1, in the entire interval between -1 and 1, it's, you know, the probability that Sn is somewhere in there is sub-exponential. It's exponential of -n times 0 plus a little log of n. Okay, so in particular, we should have that the probability that Sn belongs to, let's say, -1/2, 1/2. This should be, so if the theorem was true, this should be greater than exponential of minus little log of n. Okay. I mean, maybe a better way to write it would be that 1 over n log of this probability, the lim inf of this should be greater than or equal to 0. But in fact, it's not at all like this, because this probability is 0. Okay. This thing is 0. So when we take the log, we should think of this as being minus infinity. Okay. So problem. So problem. So if you're not convinced by the fact that here I'm using, you know, that log of 0 is minus infinity, you can fine tune this argument a little bit. You just go back to the definition of Sn, and you allow an extremely tiny probability for Sn to be equal to 0. Okay, so let's say it's with probability exponential of minus n squared, Sn is equal to 0. And otherwise, it's equally balanced between 1 and -1. Then, the entire thing I just said is still valid. And you see that this log probability will not satisfy what large deviations ask for. Okay, and the moral of the story, if you want, is that for this specific example I chose, the probability that Sn is around x, this is not a convex function of x. When we say that 1 over n log of p Sn equals x should look like psi star of x. In particular, so I have not explained that yet, but psi star is a convex function of x. And so you would have that, you would want that this thing is convex as a function of x. But the function the Sn I chose does not satisfy its property. It can be 1, it can be -1, but in between, this is impossible for Sn, or extremely unlikely if you want. Okay, and this does not occur when we do sums of variables because, yeah, okay, I should explain more, but when you do sums of independent random variables, this cannot occur because you can always make it so that maybe some part of the variables take some value, the other part take the other extreme value, and so you can realize any convex combination of these values. So this question does not show up if Sn is a sum of IID random variables. So in general, maybe a takeaway message is that in general, what is revealed when we do this psi star thing is the convex envelope of the function which is here. And when psi is C1, in some sense, it's telling us that actually this is fine, this function is really convex, so we are in good shape. Okay, so if you did not understand my heuristic comments at the end, don't worry, this is not crucial. All right, so in the short amount of time that remains, I hope to continue with displaying interesting results which I think are useful to have as a background. And so you've seen that when we discuss large deviations, there is a lot of convex analysis questions which show up. So I want to recall to ourselves a few things about convex analysis. So just to make sure we are on the same page, I'm going to only consider functions defined on RD. No, yeah, sorry, there's a question in the chat because I said that without loss of generality, I can display the statement with speed n. I just mean that you will have to relabel a sequence if the speed is not n. But in general, it's not an easy matter to determine what is the correct speed if I give you a specific sequence. It's just that once you have figured out what is the correct speed, you can apply the same result by just relabeling the sequence. But it's not. There's no magic easy way to guess it. But maybe a good practice is to try to compute these Laplace transforms and see, under which for which speeds does this have non-trivial behavior. That would be a good approach to trying to understand what is the correct speed. So yeah, for my convex analysis part, I'm going to only focus on functions defined on RD. And for convenience, I allow the function to also take the value plus infinity if it wants. And we say that this is convex if for every x, y in RD, and alpha between 0 and 1, we have that f of alpha x plus 1 minus alpha y is smaller than or equal to alpha f of x plus 1 minus alpha f of y. So yeah, the one thing which is convenient with allowing the function to take value plus infinity is that I can always pretend that my function is defined everywhere on RD, and then you can think of the true domain, if you want, or the effective domain, as it's called, of the function as those points for which f of x is finite. Okay, those points x for which f of x is finite. This is the true domain of a function. So if you take a convex function on a convex set, a subset of RD, you can always define it to be plus infinity outside, and this will be a convex extension. Okay, so you can go from one to the other without loss of generality. And perhaps it's already become clear, but a prominent example of a convex function I want to think about is if x is a random variable, let's say taking values in RD, then if you look at the mapping, okay, so from RD to R, okay, union plus infinity, which for a given lambda associates, oops, I forgot the log, this Laplace transform, log of expectation of exponential lambda scalar product x. This is convex. Well, this is a convex function. Okay, so yeah, there's a proof somewhere in the handwritten notes, but the argument is just Jensen's inequality. Okay, when you want to prove this property, you use Hölder's inequality. Hölder's inequality with exponents 1 over alpha and 1 over 1 minus alpha. So yeah, I encourage you to check this out. Okay, so another definition I want to introduce. So now I define convex function. I want to define lower semi-continuous. So we say that f is lower semi-continuous I'm going to also use LSC sometimes. If for every sequence xn converging to x, we have the following inequality. So I want that f of x is always below the limit of f of xn. So maybe this does not talk to you very much. If you know about sublevel sets, this asks that the sublevel sets of the function be closed. So graphically, maybe a drawing is always better than lots of formulas. So when you take a convex function on RD, it's always going to be continuous and in fact locally Lipschitz on its effective domain. So the things that it can only go bad at the boundary of the domain, of the effective domain. So a convex function which would not be lower semi-continuous would, for instance, look like this. So maybe you have, okay, this is the convex function. Okay, maybe it almost looks non-convex near the end, but let's say it's convex. And then at this point, the value it takes is actually above here. You know, there's no continuity at the boundary. This is the value at this specific point at the boundary, and then it's plus infinity. Then I'm going to draw like this. This is the plus infinity value. Does it make sense, the drawing I do? So if you think it's a, you can think it's a one-dimensional example. The horizontal axis is the variable, and on the vertical axis, I'm displaying the value of the function. So it's this continuous curve, and then at some point, let's say it's at 0, there is a jump for the value of the function, and then to the right of this point, the function is plus infinity. So this is a convex function, but it's not lower semi-continuous. Because if I approach this continuity point from the left, I will get a limit which is below the value of f of x. Okay, so this is not LSC, but it's easy to make it LSC by just changing the value at this boundary point. Okay, so maybe we can do like this. Okay, so I'm going to maybe, let me see if I can copy this. Oops. Maybe this, yes. So what I'm going to do is just decide that now the value of the function is just here. And then it's plus infinity. Okay, and this is LSC. Okay, so this lower semi-continuity thing is something about you know, like making sure that the guys at the boundary are not jumping away. And now let me do 2 remarks. The supremum of convex function is always convex. So this you can check from the definition. And separately from that, a supremum of lower semi-continuous function, whether or not they are convex, is always lower semi-continuous. Okay, and this perhaps, at least the way I like to think about it is using this characterization in terms of sublevel sets. The sublevel sets are closed. This is an equivalent way to say the function is lower semi-continuous. And if you think about the sublevel sets of a soup, this is the intersection of the sublevel sets. So you're taking intersections of closed sets, so it's going to be closed. Okay. And so what I'm going to so as we stand here, I want to make this observation that if I ever manage to write a function as a supremum of affine functions, then this function will have to be convex and lower semi-continuous, because affine functions are convex and they are lower semi-continuous. And the surprising thing is that this is actually a sufficient condition. Any function which is convex and lower semi-continuous can be written as a supremum of affine functions. And in fact, this is at least this is one geometric way to think about convex duality. So let me reintroduce the convex dual. So again, I'm using this this F star. Yeah, sorry, sublevel sets. Yeah, like please feel free to ask a question. Like I will not be. There's no problem with asking about pronunciation questions. I'm going to try to speak more clearly, but it's not always easy. So here I should take scalar product. Okay, this is in RD, so now it's lambda scalar product x minus f of x. This is the convex dual of the function f. And so by definition, you see that f star of lambda for any lambda and x, this is larger than lambda dot x minus f of x. So just if I rearrange things, I have f of x, which is, oh, sorry, I meant, yes, no, that's right. F of x is always larger than lambda dot x minus f star of lambda. And you see that in some sense, this f star of lambda is defined as being the largest possible value such that this is true. So you can think of, if you believe the thing I said about a convex function is the supremum of affine functions, for any slope, we are trying to find the best possible intercept, which so that the affine function still remains below the function f. Okay, so f of x, I want to find the best possible value here, which makes it so that the inequality is still valid. And so by definition, this is f star of lambda. And the theorem I want to insist upon, which I believe is really remarkable and which maybe does not look so impressive when you first see it, but in fact can really do many things for you. Yeah, I believe this is really one of the most useful results in analysis. So a function, okay, especially if you do also a variant where you don't assume that the function is defined on RD, but maybe also on infinite dimensional spaces. So here I'm just sticking to RD, but a function f from RD to R union plus infinity is convex and lower semi-continuous if and only if it is equal to its bidual. So you see that when I reach this stage here with this inequality, I mean, on the right-hand side, I can take the supremum over lambda. And the supremum over lambda, this is really the dual of the dual of f. That's what I call this bidual or bidual. Yeah, maybe later I will ask if I should say bidual or bidual. Maybe bidual. So it's clear that f is always larger than or equal to its bidual. And the statement here is that, in fact, as soon as the function is convex and lower semi-continuous, we have equality here. Okay, and yes, so this again I think is useful to know. So this I'm not going to prove it. It's not in the it's not in the notes. I did not provide a proof in the notes. So if you want a proof, you can look into. I mean, it depends on your taste, but personally, I like the book of Eklund and Temam on convex analysis. This is a D. I think it's just called, I don't know, maybe it's called Convex Analysis and Variational Problems. I like it because it's very to the point. Like, on page 5, maybe you already have the proof. Or maybe I'm exaggerating a little bit. But another possible reference is the book by Brzezinski on functional analysis. Also has the proof. Yeah, so I'm kind of running out of time, but I said the important things I wanted to say today. So today was a bit fast, but rest reassured. So ultimately, when we enter the core of the matter, I'm going to slow things down somewhat. So if you thought that was a bit too much, yeah, please stay with me for a little more. Today was to try to give these background results, which I think are interesting, but you don't need to absorb all of this in some very deep sense in order to appreciate what's coming next. Yeah, what else did I want to say? Yes, so perhaps the one useful thing you can do. So have a look at exercise 2 of problem set 1 if it's not already done, because it's in the spirit of this derivation with the Bernoulli random variable we have done at the beginning. And also, I think it's interesting to see how this Gertner-Alias argument works. So this large deviation principle, assuming that the function psi is C1, at least I find it interesting, and you can find the argument in the handwritten notes. So I think it's maybe a useful thing to have a look at. Are there questions?
Just before people start disappearing, well, thank you very much, Jean-Christophe. I wanted to remind everyone of what I wrote in email in case you hadn't checked your email or didn't get it for some reason. So we're going to have a social gathering between the two courses. And the plan is to do that every Tuesday and potentially at other times if there's interest. So I've just put the link in the chat. It's using a platform called GatherTown, which is fairly intuitive, geographical sort of interface where you can roam around a virtual room and meet with various groups of people. There is a password, I believe, which is almost surely. Here, I'll paste it in. And that link hosts up to 100 people, and it should stay active for the duration of the summer course, even at times other than those regular Tuesday meetings. So if you want to plan other meetings, you can do so. But on the flip side, please don't share that information publicly, because if spammers get hold of it and start using the meeting for their own devious ends, then we'll have to lock it down or change the password or something. Great. So sorry to interject during question period, but I thought I'd put that out there.
Yes, that's a very good idea.
Good, thanks.
And just to clarify, also, I'll be going there. Maybe I'll take 5 minutes of a break. But so if you don't show me, if you don't see me immediately, and you see, if you want to talk to me, I will be there. But just be a little bit patient, maybe for the first 5 minutes or so.
Great, thank you.